Hello, I'm Haochen, and I'm from Shanghai Jiao Tong University. Today, I'm going to present our work, Cranial Implant Design through Multiaxial Slice Inpainting using deep learning. Cranial implants are used to repair cranium defects, which may be caused by trauma or brain tumors. In practice, in order to recover the function of the damaged bone tissue and consider aesthetic factors in the same time, the cranial implants must be patient-specific, and the easiest way to meet these requirements is to make the shape of cranial implants as similar as possible to the original undamaged shape. Thus, the task of cranial implant design can be reduced to a shape completion task. One of the most commonly used cranial implant design process has the following 4 steps. First, manually determine a symmetry plane and then mirror the defective cranial model about the symmetry plane to fill the defective region. After that, the implant can be obtained through Boolean subtraction operation, and a series of post-processings is always needed to refine the implant. However, in order to get satisfying results, dedicated CAD software and sophisticated procedures are commonly seen in papers using methods like these. Most importantly, this method cannot generate the complete implant if there are defects across the symmetry plane. Nowadays, there are some methods that can generate the implant from a defective cranial model automatically, such as the statistical shape model and deep learning. For the deep learning-based methods, a combination of the volumetric convolutional neural network and the denoising autoencoder structure has been seen in a recent paper, which uses voxelized and binary-valued cranial models as input and output. However, due to the conflicts between the high demand on memory for 3D data storage and low inboard memory of contemporary GPU cards, the resolution of 3D CNN cannot be very high, which always makes the output implant to be coarse. Our proposed method predicts cranial implants through inpainting 2D slices of the defective craniums from different axes, and this is the overall workflow of the proposed method. Because the dimension of the axis varies between different cases, and consider that the size of the cranium also varies from person to person, the first step of the proposed method is resizing the skull region of each cranial voxel image into the same dimension. Then, 2D CNN networks are used to predict the implant parts of each defective slice from different axes. After that, slice inpainting results from different axes are synthesized to form an enlarged implant. In the end, through another resizing transformation, which inverts the first step, the final implant of the defective cranium is obtained. In order to regularize the shape of each cranial image, the bounding box of the skull region in each image is first calculated. Notice that the edges of bounding box must be parallel or orthogonal to the voxel coordinate axis. Besides, if the implant will exceed this bounding box region, some margins should be manually added to enlarge the bounding box to ensure that any possible implant falls into the bounding box region. Then, a simple resizing transformation is applied to enlarging the bounding box region into the same dimension. This is the network structure used to inpainting 2D defective slices. As the rightmost figure shows, it is made up of an encoder, a decoder, and an auxiliary path. Each consists of a series of convolutional layers. Arrows indicate the flow of data, and the function name-like nodes beside the arrows denote the operation blocks used, which are described in detail in the left figures. In the encoder part, with the flow of data, the image shape goes smaller, while the number of channels goes larger. To the opposite, in the decoder part, the image shape goes larger until the input shape, and the number of channels goes smaller until 1. The experiment shows that the auxiliary paths and the channel attention mechanism provided by the SDE block are helpful to improve the accuracy of the model when large defects are in the input. Note that these 3 CNN networks used to impinting slices of different axes all have the same network structure, but are trained with different datasets. For the first CNN network, it was trained with defective and implant slices taken from the x-axis only. Similarly, the second and the third CNN network are trained with slices taken from another 2 axes, respectively. Besides, the input defective images are binary valued, but the output implant images are called probability images, whose pixels take values range from 0 to 1, and higher values means higher certainty for that pixel to be part of the implant. Data augmentation is used in training networks and it's based on statistical analysis of the precision and size of the defects in slices from training cases. It works by first generating a rectangle mask for each complete slice, and then the defective slice can be obtained by masking out the mask region from the complete slice, and the rest part is the corresponding implant. In order to gain better impeding performance for all the 110 cases, different mask generation schemes are used for the first 100 testing cases and the last 10 testing cases. For the first 100 testing cases, slices of different axes have different mask generation schemes, 2 for x-axis and 1 for each other. However, for the last 10 testing cases, 3 different mask generation schemes are used for both x, y, and z axes. In the training phase, the loss function is chosen to be dice loss, and the smooth factor is 1. The multiplication sign here means element-wise multiplying of 2 tensors. In order to reduce training time, there are 4 optimizer and learning rate pairs used for training successively, and we use the loss value of validation set to supervise the training process. Starting with the first pair, when the loss value of the validation set goes higher than the lowest recorded value for 3 tolerance epochs, switch to next pair and continue the process until all these 4 pairs are all used. This is the penultimate step of our method. After stacking the 2D slice inpainting results into 3D probability voxel images for each axis, we got 3 voxel images representing implant prediction results from different axes, which are called P1, P2, and P3. The synthesize method proposed here can generate a binary valued voxel implant imaging from 1, 2, or 3 voxel images from P1, P2, and P3 based on these equations. Besides, we will get 7 different results in total, 1 for 3 axis version, 3 for 2 axis version, and another 3 for 1 axis version. Users can choose the best one and resize it back. to its true size and position. These are 3D plots of the 7 synthesized results from different axis combinations. Streak artifacts are obvious in the 3 single-axis versions, and the outer surface of the 3-axis version looks smoothest among these 7 results. Experiments show that the x and y-axis version has the lowest mean Hausdorff distance and the second highest mean dice score. So the submitted prediction results are all synthesized from x and y-axis. This is the quantitative evaluation results of the 110 testing cases, and this method has a mean dice score at about 93% and mean Hausdorff distance at 3.7 mm. However, there are some limitations of this method. Firstly, the network was only trained on datasets having straight defect boundaries, which is rarely seen in real clinical cases. Secondly, due to the nature of 2D slice inpainting, some space information is lost in the implant predicting process, which also leads to the unsmooth implant surface. Lastly, the 2D slice inpainting methods tends to fail if the defects of a slice is too large. As a conclusion, the main findings of the proposed method is that the cranial implant design can be performed through defective slice inpainting at higher resolution, and the implant projection results from multi-axis outperform single-axis versions. Besides, the future work of this method is trying to train the network on datasets with more realistic defects. Thanks for your listening.